Okay, so there's not much left in chapter 4 we need to cover. So let me just deal with that right now. I think the last time I talked about ionic compounds and their formulas. And I think I was stressing the point that when it comes to ionic compounds, there are no discrete units, there are no molecules. So the formula that you see representing any ionic compound is basically an empirical formula, which gives you the simplest ratio of the different elements present. And I think I talked about this representation of sodium chloride. The ratio of sodium ions to chloride ions is 1 to 1. And this is basically how the ions assemble themselves to form what is known as a crystal structure. And let me see what else here. Okay, so this is just a summary of the different types of compounds, molecular and ionic, and their fundamental natures. And I think this is where I stop. So basically, what this is highlighting is the fact that a formula can represent different things about a particular substance. For one, it serves as an abbreviation for the name of the compound. So instead of writing out the full name, you can just simply write the formula, and anybody who does chemistry will understand what you mean. But it also can give you the ratio of the different particles, ions, or atoms that make it up. So it gives you information about the composition. So for example, in the case of calcium chloride, basically what this tells you is that for every 1 calcium ion that is present, you're going to have 2 chloride ions, right? So that's what this represents right here. Okay, and some rules for writing down the formulas. In fact, we're going to get into some more rules in the next chapter, I think. Yeah, but for now, when a formula contains 1 atom of an element, the symbol of that element represents 1 atom, and the number 1 is not used for a subscript. So it's just understood that there's only 1 atom present beside in the formula. So for example, in the case of NaCl, right, this indicates 1 sodium ion and this indicates 1 chloride ion. And then now, if you have more than 1 atom of an element, then the use of subscripts will come into play. And we see that in this example here. So this represents phosphoric acid. And as you can see, you have a 3 here. So therefore, there are 3 hydrogen atoms indicated here. Now, this phosphorus has no number here, but it's understood to be 1. And then as far as oxygen is concerned, there are 4 of them in the formula. All right? And that's it. Okay, and we're going to get into more formulas later on, but this is just some general elementary introduction. You can have a situation where in the formula you will have a parentheses and then you have a number placed outside of the parentheses to indicate multiples of that unit represented within the parentheses. Here's an example, right? This is representing the formula for barium phosphate. And basically, this 3 here, of course, will multiply the number of atoms or ions of barium. So that will be 3 barium ions. And then you have 2 here outside this parentheses here, right? So this 2 multiplies everything within the parentheses, right? So basically that means that, well, this is called a phosphate group. So you have 2 phosphate groups, but within the phosphate group, you have a phosphorus atom and 4 oxygens. So that basically multiplies by 2 the number of phosphorus atoms, and the 4 oxygen atoms will be multiplied by 2 as well. All right. And then finally, when it comes to what the formulas actually represent, they basically represent or show the number of atoms of each element present per unit, right? They don't indicate how the atoms are actually bonded to each other, right? For you to represent that, you're going to need what is known as a structural formula, which we will get into later on when we start talking about Lewis structures, all right? And that's pretty much it for this chapter. So for this assignment, for this chapter, we'll be concerned with the composition of atoms. And if you remember, remember we said that basically within the atom, there are 3 subatomic particles. You have the protons, you have the neutrons, and you have the electrons. And just to remind you, The protons and the neutrons are located in the nucleus of the atom, and the electrons would be on the outside moving around, right? And there's some terms that we learned. I mean, I should remind you of those terms. Oh, how can I forget? You guys out there in Zoom, let me publish assignment number 4 for you guys. Okay, so assignment number 4 is now published. So you guys out there in Zoom, you should be able to access, download, whatever you want to call it, assignment number 4. All right. So what was I saying? All right. So there's some definitions that you need to recall in order to complete this table, right? The first one is the atomic number, right? The atomic number, by definition, would be the number of protons in an atom, right? And each element has its own unique atomic number, right? So if you go to the periodic table, you see that, for example, sulfur has an atomic number of 16. So therefore, you can come to the conclusion that sulfur has 16 protons in its nucleus, right? And then there's another number known as the mass number, right? And the mass number is, by definition, the sum of the number of protons and neutrons in an atom, all right? Now, I don't remember if I said this, but very often, especially students meeting this topic for the first time, confuse the mass number with the atomic mass, right? Those are two different things. The atomic mass would be the higher number of the two for each element present in the periodic table, right? Most legitimate periodic tables contain 2 numbers for each element. The lower one would be the atomic number, which I just defined, right? The higher one in the periodic table is the atomic mass, but that is not the same as the mass number. The mass number, by definition, is the number of protons and neutrons present in an atom, all right? So based on what I've just said, here you go. So based on what I've just said, for example, we can do the first line right here. Let me turn on my pen. All right. So what are you given? You're given copper. That's the name of the element. You're given a number of protons, you're given a number of neutrons, and you're given a number of electrons. Oh, another thing I should say too, and I think I said this before, but just in case I haven't. In any neutral atom, the number of protons and electrons are equal. All right? In any neutral atom, the number of protons and the number of electrons are equal. All right? Okay, with that said, we can now complete this line right here. So the symbol for copper, you can look that up, and that will be Cu, right? The atomic number, remember we said that the atomic number by definition is the number of protons, right? And we're given a number of protons here, right? So therefore we can put 29 here, right? And then now the mass number, remember we said that the mass number is the sum of the number of protons and neutrons, right? Here we have the number of protons, here we have the number of neutrons. So 29 plus 35, 64, and that would go here. And that's it. All right? And that's how you'd complete that line, right? Now, in the case of the second line, you're given the formula and the name, tin, SN. The atomic number, well, basically, in order for us to get the atomic number, you have to consult the periodic table. Now, I can't see it from here, so I probably need your help. Tin. Well, oh, yes, that too. Yeah, thank you. So this will be 50. But just in case this is not given, right, you'd have to look it up, right? But since it's given, there will be 50 right here. And then the mass number would be the sum of the, oh, and by the way, the number of protons here will be 50. And therefore, the mass number is what? 119. 119, because remember, the mass number is the sum of the protons and the neutrons. So that's 50 plus 69, and that's 190, all right? Okay, let me hear what you have to say about the third line. What would I write here? Iodine or iodine, not sure how the correct pronunciation is. Okay, what goes here? Okay, I think I lost. Oh, I have lost contact. Oh, I temporarily lost contact with the Zoom folks. Ah, come on. Okay. Let me share my screen again. Okay. All right. So let me turn on my pen. All right. So somebody said I should write iodine here, which is true. Okay. What do you think goes here? 53. What goes here? 74. 74? Yep. And what goes here? 53. Exactly. All right. And that's basically how that's the approach you take, right? It's just based on the definition. Yes, ma'am.
What's the formula to find the neutrons?
Oh, that's going to be the difference between the mass number and the atomic number. All right? The difference between the mass number and the atomic number will give you the number of neutrons. Yes, sir.
You said atomic number can be, is what equals the number of protons?
Right. By definition, the atomic number is the same thing as the number of protons.
Wouldn't that mean, but you can also find out how many protons you have by how many electrons you have.
Exactly. But that is in a neutral atom, which we're assuming in this case.
For neutral.
For a neutral atom. Later on, when we start discussing ions, you're going to see that's not the case.
So if it's neutral, you can also say the atomic number can be found to the electron.
Exactly, right. Because in a neutral atom, the number of protons and the number of electrons are the same. Yeah. All right, so what I want you guys to do is to complete this table, right? And I'm here if you need any help, if you have any questions in any one of these. That's why they pay me the big bucks. You notice the sarcasm in my voice. Yes, sir.
Sir, you already said it. How did you find the neutrons again?
Right. The neutrons, the number of neutrons will be the difference between the mass number and the atomic number. Because by definition, the mass number is equal to the sum of the neutrons plus the protons. Right? So if you know the mass number and you know the atomic number, which is the number of protons, the difference will give you the number of neutrons. Yeah. Here you go, lovely lady.
Or me?
I have to do it. Yeah, so we're working on that. You need to be familiar with the definition of the atomic number, mass number, and so on. So if you have any questions, just let me know. Yes, sir. I'm sorry? Where we?
Or nickel.
Oh, nickel. Oh, where's it? So nickel.
30.
Oh, let me clear this first.
Oh, yeah.
Nickel. Oh, nickel. Okay, what about nickel?
There's
30.
no new funds or mass number listed, so I can't just fix.
Okay, so in that case, oh shoot. In that case, you're saying that there's no mass number, there's no.
Mass number or neutron.
you know, mass number or atomic number or number of neutrons. Oh, okay. So guess what? That means that you have to leave those blanks or put NA because in order for you to know what the mass number is, you need the number of neutrons and vice versa, right?
Yeah.
So since you have neither, then basically you're just gonna leave those blanks. So everybody heard that in the case of nickel? I'm sorry, folks, you folks out there in Zoom, for some reason, the Wi-Fi here is, let me try to, get this back up so I can share my screen. Okay, so he was mentioning, okay, where's nickel? Okay, here's nickel, right? And according to what we have here, the information provided, well, what's not provided is, the mass number and the number of neutrons, right? So basically, you cannot determine one without the other. In order for you to determine the mass number, you need the number of neutrons and vice versa. So therefore, what I would do if I were you is that I would put something like Na here and Na here. Because it's simply impossible to determine one without the other. All right? And I think there's another one further down like it. I forgot which one it is. I'm quite sure you'll find it.
I think it's platinum, because you only have the map. Neutrons or leptons.
No, platinum,
Yeah, you could just look up the.
platinum, they gave it a mass number, that's not it. But I think there's another one. Oh, okay, I see it. The other one is this one right here. Your mass number is not given, and the number of neutrons is not given. So that's another one where you cannot determine one or the other. And I think, oh, and calcium too. Who said calcium? Calcium too, yeah, you're right. Calcium, you're not given the mass number and you're not given the number of neutrons. So you cannot determine either. Okay, are we anywhere near finished?
Yeah.
Hmm? Oh, cool. All right. So, what I'm going to do is, as usual, create a Dropbox for this assignment. So this is assignment number 4. And, oops. Okay, so I'm going to set the deadline for tomorrow. Okay, so you can now submit that online. All right, so let me go to the next chapter, chapter 5, And that chapter is dedicated to learning the rules for naming compounds. So hold on, let me for the benefit, oh, it's already published. All right, so let me click on that. So you guys online can access that PowerPoint. So nomenclature, that's what this chapter is all about. How do we name compounds? The rules for naming compounds, all right? And as you're going to see, the type of rules is dependent on the type of compounds that you're trying to name. So basically, there are two types of names when it comes to compounds. You have what are known as common names, and then you have the systematic names. The common names basically is very more arbitrary, right? In terms of how we go about naming compounds, because sometimes they're based on anything but the composition of the compound, all right? They may be based on, for example, an outstanding physical or chemical property, all right? So even though the common name might be a bit descriptive, it does not give any information necessarily about the actual composition of the substance, right? What would do that is what we call the systematic names, right? And basically the systematic names can help you, if you know the rules, to determine the composition, the elements that make up that particular substance, right? And there's an organization known as the International Union of Pure and Applied Chemists, right? And there's a division within that organization that meets, if I remember correctly, every, I think, 2 years or 3 years. I don't remember exactly. And that committee that meets basically meets for the sole purpose of coming up with rules for naming compounds, because every year new compounds are being made, and very often what happens is that the new compounds being made cannot be named according to the rules that have been established so far. So therefore the committee has to come up with new rules for accommodating these new compounds. So basically the rules that we're going to discuss has been established by this organization, the International Union of Pure and Applied Chemists, all right? So just to give you an idea, and this is without even you guys knowing all the rules, the difference between the common names and the chemical names. For example, for this compound here, CaO, that's a formula, the common name is lime, but the chemical name is calcium oxide. And you can clearly see that from the chemical name, it gives you some idea. Even if you don't know what the rules are, it gives you some idea as to the composition. Calcium and oxygen is present in that compound. Lime doesn't tell you anything, right? Lime just basically is a common name that's associated with that substance. And you can do the same you can see other similarities when you compare the common names to the chemical names for other compounds, all right? So let me talk about firstly elements and ions. So basically, we know about formulas that are used to represent elements. Here are just some examples, right? So the formula would represent it is a symbol for the element. And then you have 7 elements. I don't remember if I told you this before, but there are 7 elements that exist in nature as diatomic molecules. In other words, they exist out there in nature as 2 atoms per molecule, right? You need to memorize these, right? These 7 elements, all right? 4 of which are from group 7A, the halogens. And the rest of them are hydrogen, nitrogen, and oxygen. These are the halogens, fluorine, chlorine, bromine, and iodine, right? So you need to memorize these elements as diatomic molecules, all right? Also, there are some other elements that exist as polyatomic ions, namely sulfur and phosphorus. So sulfur exists as 8 atoms per molecule, and phosphorus exists as 4 atoms per molecule. Again, you need to memorize those, all right? Okay, so let's talk about ions, all right? What are ions? Basically, an ion is a charged particle which is formed as a result of an atom either losing or gaining electrons, all right? So you're starting from a neutral atom, and the neutral atom may either lose or gain electrons. Now remember we said that in a neutral atom, the number of protons would be equal to the number of electrons, right? That's what happens in every neutral atom. So when an ion is formed, that will not be the case, right? if you remove an electron from an atom, then basically the number of protons will be greater than the number of electrons. And if the atom gains electrons, then the number of electrons will be greater than the number of protons, right? So we're going to see what happens in each of these cases, right? So the example which is being shown here is the potassium atom. The potassium atom has 19 protons and 19 electrons. Now, potassium, like other metals, they tend to lose electrons, right? So we have 19 electrons here, and then when one electron is removed, you're going to end up with a structure which now has 18 electrons, but still you have 19 protons, right? So therefore, this will not be a neutral particle anymore. In fact, what will happen is that this particular ion that is formed will now have a plus charge because now it has one more positive particle compared to the number of electrons, all right? So therefore, this is called the potassium ion, and the symbol is K with a plus sign written as a superscript. Now, positive ions, there's a general name for these ions. They're called cations, right? So any ion that has a positive charge, they're called cations. So therefore, this is a potassium cation, all right? So that's what happens in the case of potassium. So, okay, so I just said that. A positive ion is called a cation. All right, so that's just one example. And there's some other examples that I'm going to have listed here, right? So sodium, for example, will lose one electron to form a sodium ion. The calcium atom will lose 2 electrons to form a calcium ion. And you'll notice a pattern emerging here. In the case of the sodium ion, it has 1 plus charge, right? Because it lost 1 electron. In the case of the calcium, it has a plus 2 charge or 2 plus charge because the atom loses 2 electrons. And then in the case of aluminum, it loses 3 electrons. So therefore it carries the ion that is produced will carry a plus P charge, right? Now, you might be wondering what determines the number of electrons that would be lost by an atom. We're going to get into that later on, all right? But for now, basically you can just accept what I've stated here, all right? Okay, how do we name cations? How do we name these positive ions? Well, it's relatively simple. Basically, the cations are named the same as their parent atoms, all right? So for example, the sodium ion that is formed, it is simply called the sodium ion because it's formed from the sodium atom, all right? Calcium, when it loses the electrons, forms a calcium ion. Lithium forms a lithium ion. So it's very simple. Whatever the name of the ion is, or I should say, whatever the name of the atom is, the name of the ion will be the same. Here's another example. Magnesium will form the magnesium ion. Strontium would form the strontium ion, right? So basically that's how we name these ions. All right, so that's as far as the cations are concerned. What about the negative ions, which are known as anions, right? Basically, those are formed when an atom gains 1 or more electrons, all right? So the example we're going to use here is the chlorine atom. The chlorine atom has 17 protons and 17 electrons. And what will happen is that the chlorine atom, which is neutral, will gain an electron, right? And therefore, the total number of electrons would be 18 electrons. You still have 17 protons in the nucleus, right? And as a result of an electron being added to the atom, the resulting ion will have a negative charge, and the name of this ion, well, this is not an ion, all right? Now, the names for the rules for naming anions kind of different from naming cations, all right? Basically, you start off with the stem of the name, the first part of the name of the particular element, and then it ends with IDE, all right? So in the case of chlorine, it becomes a chloride ion, all right? Now, in this case here, we're talking about fluorine. So when that gains an electron, it forms a fluoride ion, all right? So you have the stem of the name of the element, and then you have the IDE ending. Chlorine becomes the chloride ion. Bromine becomes the bromide ion. Nitrogen becomes the nitride ion. And phosphorus becomes the phosphide ion, right? So that's basically how these ions are named. Oxygen becomes the oxide ion. So that's basically how the anions are made. You add an electron or two, and therefore the name would be the stem of the name of the original element, followed by IDE, all right? Okay, so this is saying ions are always formed by adding or removing electrons from an atom. Most often ions are formed as a result of the combination of metals with non-metals. And to some extent, the charge on the ion can be predicted based on the relative position of the element that forms the ions in the periodic table. And this is just a summary of some of these ions. What you'll find is that elements belonging to group 1A, which is a furthermost left group or column in the periodic table, they tend to form ions with a +1 charge. Elements in the second group here, they tend to form elements, or I should say ions with a +2 charge. And then over here, the elements in group 7A, they tend to form ions with a -1 charge. Elements in group 6A, they tend to form elements, I keep saying elements, they tend to form ions with a -2 charge. And then elements in group 5A, they tend to form ions with a -3 charge, all right? Beyond those two extremes, things are a bit hazy in the middle. It's very difficult to make predictions as to what type of ions or what type of charges would be formed, all right? Okay, so let me next talk about how do we write the formulas based on the names of the ionic compounds and vice versa. We're going to see how we can write the formulas based on the names and write the names based on the formulas, right? The key important thing that you need to remember when it comes to doing this exercise is that the entire compound must be neutral. What does that mean? That means that the total negative charges contributed from the anions must be equal to the total plus charges from the cations, all right? So basically all the charges as a result must add up to 0, all right? So let me illustrate by using these examples. And by the way, I don't know if I told you this, but in Canvas, there is a document which has things like the periodic table and so on, right? And there are 3 pages which has a list of common ions, right? You're going to use that in exercises like this. In fact, I'm going to make that table available to you during your exam. So, you know, my philosophy is when it comes to these things, you don't need to memorize these ions, right? You'll have access to it, you can refer to it so that when you're doing questions like these, you can use it to help you to answer these questions correctly. So, let's start off with calcium chloride. So if you're asked to write down the formula for calcium chloride, you'll consult the table, right? And if you look it up, you'll see that calcium has a charge of +2. So I'm going to write Ca2+, right? That's a formula for the calcium ion, right? And then now for the chloride ion, if you look it up, you see that is Cl-. It has a -1 charge, all right? So you have identified the ions. Now the question is, how do you put this together? Remember what I said earlier. The total number of plus charges must be equal to the total number of negative charges, right? As it is right now, that's not the case because you have a +2 charge here and you have a -1 charge here. So the question now becomes, how do you get the charges equalized? And the answer is you multiply this by 2. Because by doing that, you now end up with 2 negative charges, which will exactly cancel out the 2 plus charges. So when you put this together, the answer, the final answer will become CaCl2. In other words, this 2 here becomes the subscript for chlorine, or chloride, I should say, in the formula. And that's how that is done, all right? Any questions about that example? Any questions? Any questions? Okay, so for the next one, you're given barium phosphide. So again, you'll consult the table, and when you look up the formula for the barium ion, it is Ba2+. And then when you look up the formula for the phosphide ion, it is P3-. All right? So the question now becomes again, how do you get the charges equalized? Because you have a +2 here, you have a -3 here. In this case, what you do is multiply this by 3 and this by 2, because 3 times +2 gives you +6, and 2 times -3 gives you -6, right? So the charges are now canceling out each other, So the final answer becomes Ba3P2. And that's it. All right? Any questions about this one? Any questions? Okay, so in the final one here, magnesium oxide, again, you'll consult the table. And when you do that, you'll see that the formula for the magnesium ion is Mg2 plus. And the formula for the oxide ion, when you look it up, is O2 minus. Now, in this case here, they're both equal, right? So you don't need to multiply one of them or the other by anything. So basically, all you have to do is put these together, and the answer is MgO, and that's it. And that's basically how you determine the formulas based on, determine the formulas based on the names, all right? And if you understood this, then you should be able to do the reverse, right? If you're given the formulas, then you can determine what the names are. So basically when it comes to, oh, by the way, these compounds, they're called binary ionic compounds. Binary ionic compounds, right? They're called binary compounds because they consist of two elements, right? So that's why they're called binary. And they're ionic because they're made up of ions, all right? So binary ionic compounds are what these compounds are called. So basically, to review what I just said, basically, you're going to start off with the name of the cation, right? So the cation is named first, right? And then you follow that up with the nonmetal stem, and then it ends with IDE, all right? So I think I have a summary of it right here. Name of metal, then the stem of the nonmetal name, and then you have the IDE ending. That's basically what it comes down to, all right? And there's something that is mentioned in the slide just before this one, which says that in this system, we are not indicating the number of atoms of each element. That's very important because later on, when we're dealing with molecular compounds, you're going to see that you need to indicate the number of atoms of each element present. But in the case of ionic compounds, according to the rules set forth by IUPAC, you don't need to, or you should not indicate the number of atoms of each element present. All right, so this here is a summary. What you're looking at here is a summary of how you go about naming binary ionic compounds. So for example, in the case of CaF2, the first part is calcium, right? And the next part is fluoride, right? So the name of the compound is calcium fluoride. And that's it. All right. Just to highlight a couple more examples, NaCl, that's sodium chloride, the name of the metal, then the stem of the name of the nonmetal, and then IDE. This one is magnesium chloride. This one is potassium oxide. This one is sodium phosphide. And so on and so forth. Now, this here is a list of the different monatomic ions, how you derive their names from the corresponding element. And in each of these cases, you start off with the stem of the name of the element, the first part of the element, or the first part of the name of the element, and then all of these end with IDE. All right? Okay, and these are just some examples of binary ionic compounds: aluminum chloride, aluminum oxide, magnesium bromide, and so on. Okay, so with that said, let me get you started with assignment number 5. Sound, that's for you. Sound. You. You. 1, 2, 3, 4. Okay, and for you guys out there in Zoom, I am going to publish the assignment that I just handed to your fellow students here in person. So let me okay, let me go here. Let me go here. And then let me go here. And Okay, so assignment 5. Oh, and by the way, for you guys out there in Zoom, I'm going to publish this as well, which says that chapter 5 addendum. So that's just an extra page or two to assignment 5. So for now, I want you guys to focus on, oh, let me pull this up here. I want you guys to focus on part A, right? So in the case of part A, it says, give the formula and the name of the compounds formed between each pair of elements listed below, all right? So for example, let me help you guys out here with maybe the first couple of these. So for example, in the case of the first one, right? What I would do, I would make sure that I have the table, right? So you can pull it up on your devices, which I've published in Canvas, right? So what I would do is look up the formula for the beryllium ion, and if I do that, I'm going to see that the formula is Be2+, right? And then I will look up the formula for the fluoride ion, and that would be F-, right? And if you're called,
It's fluoride.
hmm?
Supposed to say fluoride?
No, beryllium. Beryllium. Okay.
So I think she's talking about beryllium and fluoride, but it says fluoride there.
It's beryllium and fluorine.
Fluorine?
Yeah, but the name of the corresponding ion would be fluoride, remember?
Oh, yes.
Right, you start off with the stem of the name of the element and then it ends with IDE. Okay. Right. Okay, so if you remember the example that we worked earlier, we need to make sure that the charges will cancel out. So if you remember in this case, you multiply that by 2, right? So that you end up with 2 negative charges, which will cancel out the 2 plus charges. So the final answer is going to be BeF2. And what do you think the name of this compound is? Beryllium fluoride. And that's it. All right? Okay, any questions about that one? Any questions? Any questions? All right. Okay, so let me hear what you have to say about the next one, potassium and sulfur. So what will be the formula for the potassium ion? K plus, 1 plus charge. And what about the sulfide ion?
S2 negative.
S2 minus, very good. So what's the next step?
Multiply K by 2.
Multiply the K plus by 2. So the final answer as far as the formula is concerned is what? K2S. And the name would be?
Potassium sulfide.
Potassium sulfide, exactly. All right, very good. So what I want you guys to do is to complete this table. All right? And I'll be here to answer any questions if you encounter any difficulties.
Yeah. There's one tree.
How's it going? What's up?
I'll take the test.
Oh, you should,
Or you wanna come later?
yeah, 1 o'clock would be a good time upstairs. I'm in room 218C.
2-1
218C, right.
What time do you want?
Well, I'll be there from 1 to 5.
Well, do you want after this class then?
Hmm? I'm sorry, what am I saying? 2 to 5. My days mixed up. I'm sorry. Yeah, my days mixed up. 2 to 5, yeah. 218C. Yeah, sorry about that.
This one has this one has a goal. We're supposed to, the numbers of which direction we see. So. I don't know, we said it's something she said next to me. But that's not how to do. So I just said she wants to.
Give out after 5, can I get you?
For Chem 1,
Yeah, be here.
well, we started it,
Why not? I think you passed it out, I just wasn't here.
what's that?
You may have passed it out.
Oh.
I wasn't here.
Oh, yeah, yeah. Yeah. So far, I told the class to do all the questions up to question number 7. I'm going to post the video so that you can,
Yeah, so I won't be here next week. You think you're gonna pass out chapter 6?
I'm not sure, to be perfectly honest. I may, if that's the case, I'm just going to post it online. Yeah.
So sometimes they want you to balance it to this group. But so that how we want to be too fun. But most of it are sometimes in line, so you have groups of those. So they're all trying to move the soil. They're all trying to be. Yeah, none of that's on the description. Yeah, so that's how you do it. In case you can see them, like they don't sense that all your. Because you should have to see the photo. Oh, you should see the glasses. Because he made us do, like, he made us know.
Shows.
He did not. I mean, I feel like we got the ones and I'm gonna get very first. It's in the names.
No, this one tells
I
you.
feel like the more you track it, the more there's one, I feel like you memorize it. Like we have, I thought it's the things that we.
Yeah.
Yes. And then he would give us all
All of this is here.
like we have to, like, because it will come back out. It's right there. So we can just try.
In this time.
It's a little bit. He's made it all that he's always not calling me that issue. Yes,
I was thinking if I told you.
I had them out. I had
I should get to I'll go back. I wanted to take the 6th grade ones together right now.
Yeah.
But now actually it's just bringing the sit down for 1 year.
Yeah,
Okay, that's this. And we still need to take this. Yeah, because I'm gonna hear you know, there's something that you're gonna say. Okay, so you should be. Moving the sisters.
It says yes.
So it's oxide 0 to minus. Smoke. Smoke, that's the bubble.
We'll see.
Oh, maybe that's 0. It's like.
Okay, are we finished or almost finished with part A? Almost. Well, let me give you a couple more minutes because I want to get to part B.
This consequence.
I really like to fix some lunch and meters. Okay, I want to see you right like that with every test. And with every test. Like this, and then like this. Every
Okay, so let's continue our discussion of nomenclature. Now, things can become a bit more complicated, unfortunately, because you can have some cations, positive ions, or I should say, I'm gonna put it this way. You have some elements, some metallic elements that can form cations of different charges, all right? So we have to take that into account when that happens. And there's a system, well, there are two systems that takes that into account when it comes to naming these compounds containing those kind of ions. There's one system that is known as the stock system. And to illustrate that, we're going to talk about, for example, the ions formed from chromium, or the ions formed from iron, or the ions formed from copper, right? As you can see here, for example, in the case of chromium, there are two types of chromium ions. There is one type that carries a +2 charge, and then there's another type that carries a +3 charge, right? So we have to take that into account when these ions are involved, all right? And another example is iron. It can exist as a +2 ion or a +3 ion, all right? So those are some things that we have to look into and take into account when you're naming these compounds, right? So just to illustrate what happens in the case of iron, if you're dealing with the +2 charge iron, right? When it combines with a sulfide ion, it becomes this, right? But if the charge is +3, when it combines with a sulfide ion, you see the formula is a bit different, all right? So the question is, how do we name these two? Because believe it or not, these two are the two different compounds, simply because the compositions are different, right? So basically, if they're different compounds, they must have different names, all right? So according to the stock system, basically what we do is that we use to distinguish between these ions, we use Roman numerals within parentheses to indicate their respective charges, right? So these are the charges, and these are the corresponding Roman numerals, all right? And the Roman numerals must be placed within parentheses in the name of these ions, all right? So, and of course, if we're dealing with binary ionic compounds, as we said before, the ending of the name of the compound would be IDE. Okay, so this is a stock system here. For copper with the +1 charge, we call that copper 1. But the copper with the +2 charge, we call that copper 2. All right? Iron with the +2 charge, we call that iron 2. Iron with the +3 charge, we call that iron 3. Lead with the +2 charge, we call that lead 2. Lead with the +4 charge, we call that lead 4, and so on and so forth. All right? Now, this one is a bit different, right? Mercury with a +1 charge. Now, you might be wondering, okay, it has a +2 charge, but there are two of them, right? It turns out that the actual structure of this ion is made up of two mercury atoms, and then that unit carries a +2 charge. So basically, it's tantamount to mercury 1. That's the name of that particular ion, right? While mercury 2 is simply Hg with a +2 charge, all right? So basically, that's the stock system. So you have to include the Roman numerals within parentheses to indicate the charge of the particular ion when you're writing down the name of the compound that contains that ion, all right? So let's look at some examples, right? FeCl2 versus FeCl3, all right? Now, what you'll have to figure out is what are the charges carried by the iron in each case, right? How do we determine that? Well, that is based on the fact that in this case, you have 2 chloride ions, and in this case, you have 3 chloride ions, right? If you have 2 chloride ions here, and the entire compound is neutral, that means that the iron here must have a +2 charge. On the other hand, if you have 3 chloride ions here, each carrying a negative charge, that means that this iron here must have a +3 charge, all right? So basically, when it comes to naming these compounds, this is called the iron 2 ion, and Fe3+ is called the iron 3 ion. So therefore, the name of this compound, the first one is iron 2 chloride, right? And the name of the next compound is iron 3 chloride. And that's basically how you go about naming these compounds. So when it comes to these particular type of ions, you have to be careful. You have to figure out what charge is carried by each of them, and you indicate that charge in the name of the compound. All right? Any questions about this? Any questions? Any questions? Okay, I think I have another example lined up here. Okay, yes. So we have SnBr2 and SnBr4, right? So again, we have to figure out the charge that is carried by tin in each case, right? The bromine in each case carries a -1 charge. So therefore, we can figure out that the charge carried by the tin here would be +2, and the charge carried by the tin in the second compound would be +4, right? So the name of this ion with the +2 charge, we call that tin 2. And the name of this particular ion, which carries a +4 charge, we call that tin 4, right? We have bromide in each case, so therefore, when you put the names together, the name of this compound would be tin 2 bromide, and the name of the second one would be tin 4 bromide. And that's basically how that works out. All right? Okay, now there's another system that is used in conjunction with these type of ions. It's not as straightforward as the stock system. They call it the classical system. And this is a holdover from, when the system was used back in the day, all right? And basically, the classical system is where the name of the metal is modified with the ending OUS or IC. Now, the OUS or IC does not give you exactly the information for the charges. Basically, what this tells you is that the ion that ends with the IC ending has a higher charge compared to the one with the OUS ending, right? So OUS would be the lower charge ion, and the IC ending would correspond to the higher charge ion. And the nonmetal name ends with IDE, as always in the case of binary ionic compounds. So we're going to look at the same examples, but this time we're going to apply the classical system. So basically, the one with the +2 charge, that ion is actually called ferrous, right? While this one with the +3 charge is called ferric. Again, the ending doesn't give you the indication as to what the charge is. All you can conclude is that the ic has a higher charge compared to the OUS. That's pretty much it. So it's not as useful as in the case of the stock system, all right? So the name of this compound is ferrous chloride, and the name of the second one is ferric chloride, all right? And that's it. Here's another example using the tin example that we saw earlier. This one is called stannous bromide, because this is called the stannous ion, and this is called the stannic ion. Again, ic has a higher charge compared to OUS. So this is called the stannous bromide, and this is called stannic bromide. All right, so that's it. So this is basically a list of the common classical ions and their names. All right, but to be perfectly honest, the stock system is more often used than the classical system. And that makes sense because the stock system is more useful in terms of actually predicting the charge on the ion. All right. Okay. So with that said, going back to, where's my copy? You know what, let me just bring it up here on the screen. Okay, so going back to your assignment now, we should now be able to do part B. And in part B, you're asked to name the following ionic compounds in the first part, and I think the second part you're asked to write the formulas. Yes, okay. So in the case of part B, you're asked to write down the name, right? So again, you're going to have the use of the list of common ions in the tables, right? So for the first one, the name of this compound will be calcium and then chloride, and that's it. Now you might be wondering, why don't I call it calcium 2 chloride? Because after all, the charge is +2. And the answer is that calcium only displays or only forms an ion with a +2 charge, right? So in other words, you'll never find a calcium +3 or calcium +4. It's simply calcium +2, right? And according to IUPAC, if there's only one type of ionic charge for a particular metallic element, then you don't use the Roman numerals, right? You only use the Roman numerals if there exist ions of the same element with different charges, like iron 2 plus and iron 3 plus. You see what I'm saying? So therefore, the name of this compound is calcium chloride. Now, in the case of the next one, right, the name of this compound would be iron 2 nitride. All right? And that's because the iron in that case carries a +2 charge, and also iron can have +2 +3, right? So you have to make a distinction as to which one it is. And in this case, it's going to be +2, right? Now, how do I know it's +2? Because the nitride ion has a -3 charge. And if there are 3 of these iron and there are 2 of these, that means that the charge carried by the iron here must be +2, right? Because 3 times +2 gives you +6, which cancels out 2 times -3, -6. All right? So the charge carried by the ion in this particular case would be +2. And therefore, the name of this compound would be iron 2 nitride. All right?
So,
Excuse me. Yes, ma'am.
so you only have to do the Roman numeral if the two things you're combining are both equal? So like they both add to 6 or they cancel each other out?
No, you use Roman numerals if you can have more than one ion of that element with different charges. So like in the case of iron, you can have +2 and you can have +3.
So you have to specify which one.
You have to specify which one, and that's how you do that. Exactly. Okay, so let me hear what you have to say about number 3, TIBR3. What do you think the name of that is? And again, you're going to need a list from your tables. So what do you think the name of that compound is?
Titanium bromide.
Well, you're partially right.
Sorry, it's titanium, yeah, 3 bromide.
Titanium 3 bromide.
No, 2, so.
Because titanium can exist as, if I remember correctly, +3 and +2. I could be wrong. So you have to again specify which one it is. All right. What about number 4?
Copper 1 phosphide.
Copper 1 phosphide is indeed correct. All right, so I'm going to leave you to now do the rest in part B. And again, if you have any questions, please let me know.
Yeah. Probably one. So. So what is it? So. Yeah, there's no. Yeah.
Yeah,
Number 6,
number 6, okay,
is it gallium-1 arsenide or just gallium arsenide?
just gallium arsenide. Because I don't think gallium, if you look in the table, I don't think gallium can display more. I'm sorry?
It's a mixed ion, so-
Right, exactly, +3, I think it is, yeah.
But if we put Roman numeral 1, would you take this off?
Yeah, it would, according to IUPAC, if there's only one, well, firstly, one would not be the appropriate number, but in any case, if there's only one type of ion that can be formed from the metal or from the element, then you should not use any number.
Okay, so if I just cross it out.
Yeah, cross it out, yeah. Because according to IUPAC, you only use Roman numerals if the element can display more than one charge as an ion.
It's just nice.
Yeah.
No, because there's values to two, values two, and then two. Yeah, you get to them two. So. We're gonna cancel. It's two.
And so far cancel out. Is pretty much stuff.
And my trade.
It's for many days.
Oh, yeah.
Two and four.
That is
So how would you know which one? You're not using it, but this is one. Wait. So this doesn't question.
Okay, so then two.
Oh, yeah. How do you know?
Two is also three. This was four, right?
That's six.
It's like.
Just says that. Yeah, because you would take the kids and they also get some three parts, you look at all that. This is it. You're gonna put a relevant six out. The only thing to do is like the ones that say. Don't ever do it.
So what if
So
you?
we have to show and also it has to be success.
Value
So what if you?
goes here. No, it has a 3 or 5 charge, but my charge has a 3 charge. So it has
Four. Because you just have one. Yeah. What is it? Four. Yeah. Yeah, because the ion itself is and it's wants to. There's itself.
This one? Basically, I was like, that's so messy. And then I was like,
Maybe you have. The cylinder, so you.
six.
So. Okay, so, yeah, this might go forward. So I guess, yeah, you're right. That's just fine. You guys.
Six.
I got it. Yeah, bro.
Okay, so this is one after 5, which is 6, and this is one before 5, which is 4.
Should I? Good chemist too.
Huh?
No, it's called. Or 3, D5. Yes, yeah.
Yeah, so so 6 are 3,
But it still doesn't.
P6.
The derivative from the phosphate. The rate from the phosphate. And it takes the 6 from the. Phosphorus, the phosphorus. That's the data. Because this is still a charge, so you still keep this 6, you just keep it. And it's way that you.
So if this is finding the charge, then. You still have.
Yeah, it makes sense, I just. Because you're not.
Because you're not putting them together like.
This.
Like this.
Phosphorus, it's allowed.
This, you don't.
No,
it's
it's
strong.
I'm pretty sure.
Okay, so are we finished with part B? Hmm? Oh, yes, there's,
No, except for the 2.
yeah, the second half here.
You cancel, so if I have 2.
But when it cancels, you don't write it. So, but they wrote it, so it doesn't cancel. Yeah, so then when you write it, you don't have to. Because when it cancels out, you have to, then there's this bigger charge.
Or so the phosphide has. The charge.
Which makes it with the charge of 2.
So it's the SN2, so it's phosphide. This is CR, so it would be easier. So it is N2 S for protein.
See.
So we're same thing with nitrite, same thing with sulfites. Right, this is.
Versatility.
So the phosphates, yeah, phosphorus 6. Oh, and then chromium 3.
So SN has a charge of 2 or better. So they used the set charge and it was a market level percent further.
Oh, okay.
Here it is. As it.
Yeah, so is chlorine you put that in for right?
I guess it did with 4.
That's the night drive. I didn't think you said. I didn't realize.
Yeah, smarter than
Yeah. Yeah. That's so quite a student, because
I guess if it's this one, then it's 2. So then when they read it, there's the 10.
I think they're just giving us the charge data. Yeah, trying to. So then how do you know which one is yours? So. It's okay, so. That. So. All you have to know is that the charging time. So the charging time travel. What's the. It's this. So, right, then you need to. No, this. But what about the. That's for. If I ask them to translate this, over it's the letters.
It kind of really makes us feel like. It's already have a little it doesn't hear to make her.
Okay, I'm going to stop here for today. And next time when we get back, we'll be discussing how we name compounds containing polyatomic ions. So that's for next class. Yes.
You said these two are due tomorrow or
Chapter 4 is due. Let me see here. This is due tomorrow, chapter 4. So chapter 5, we're not finished with it yet, so you can hold on to it until next class. You too.
I think so. I'm not really. Yeah, get themselves in this there and all of that, so. Yeah, or general comfort, someone.
Okay, and you guys out there in Zoom, I'm signing off now.